everybody. Well, I'm not sure if everybody is the right word. I have no idea if anyone is watching. This is kind of a weird time. But we'll see. So, my plan is to talk a bit more about how CPU in particular pipelines work, like a bit more currently than the kind of stuff you see in many computer architecture textbooks or university courses, since they tend to be, for good reasons mostly, be based around fairly simple late 80s microprocessor designs, and things have gotten a bit more complicated since then, but a few things have also gotten simpler. So last time, see if I have this page still. Like I got to this thing, like with this whole front end back end split, and so I have like here a FIFO with where the tentative instructions are inserted. So at this point, this is just a prediction from the branch predictor. We don't actually know if these are the instructions we should be executing. We're just guessing. So this is actually, as soon as you have any sort of branch prediction, you're into speculative execution territory, where you're starting to execute instructions before you know whether the quote-unquote actual flow of execution ever gets there or not. And that further down that path are things like, again, making headlines like Meltdown Inspector. So that sort of stuff is happening. If you're still in a basic in-order pipe, it's not as much of an issue. So it's not as critical here yet. But we gotta be careful here. So the other thing that can happen, or not that can happen, the other thing we need to note is all these late 80s, early RISC designs that you tend to see in university courses are single issue CPUs. They're designed so they can issue a new instruction every cycle, but they issue exactly one instruction every cycle. And the designs you actually see in practice now, unless you're really, really at the low end, tend to be superscalar designs. That is, they're more than scalar, they issue more than one instruction every cycle. They usually have some types of multiple pipelines. So what's happening, and I've updated our hardware here, let's see, is that actually you have like this here, the execution units, you have plenty. And like each of these is like, say you have ALU 0 here, you have ALU 1, like you typically have two of these. Whoops, I do that again. So you have two integer ALUs that can do basic integer operations, say, and then you say have a third like load store pipe. Say that's our design. So you have three pipelines that things can go. Like, and when I'm drawing this kind of design, that's already buzzing towards a more modern thing. So like this is a bit of an aside, but like if you look at, I'm gonna go to a different page here. If you look at older CPUs, like what do we have that's good here. 1 second. So for older designs, let's say something like the 68060 or Pentium 1. They're not designed like this, where you have different, like you're grouping these pipelines by different functional units. Instead, like for example, let's say Pentium 1, because that's one I'm more familiar with. I didn't do much on 68K. On Pentium 1, you have the U pipe and the V pipe. And the rule on the Pentium 1 is that the U pipe can run every instruction. So U pipe can run everything. And the V pipe can run some things. Like the more common operations, integer, arithmetic, whatever. That it's the kind of stuff that you would have supported on the U pipe. On the V pipe. And there's some special things like, whoops. Sorry about that. The idea in the Pentium design, and I believe the 68060 was very, very similar. Is that like I think like they were even called similar like this. In the 68060, I believe these things were called operand execution pipes. What's the terminology? So yeah, but they're like I think S and T or P and Q or something like that. They even have a similar thing. You just need to give these things names, and it's just some random letter here. The idea here is that every cycle, the CPU in these old but already superscalar designs, the CPU tries to find 2 instructions that can execute together. And the idea is that because the U pipe really can run absolutely everything, like there's never, like you're always gonna find something that the U pipe can do. That might, like some instructions cannot pair with something else, and then what's happening on the U pipe might mean that you can't issue anything on the V pipe, but everything can execute on the U pipe. So the whole idea is like every cycle the CPU tries to find something to do for the U pipe, and then sees like, oh, can I smush the next instruction after that into the V pipe? And if so, good, and if not, oh well. But there's various conditions inside the processor, like when things stall and get re-executed. That's the kind of thing I'm going to talk about today, like stalls, interrupts, those kinds of issues. The rule in these kinds of architectures is that whenever something goes wrong in this pair, and it's like these things happen simultaneously, so if there is some badness going on in here, the idea is always going to be you execute first, you execute first the U pipe instruction and second the V pipe instruction in separate cycles. And the V pipe instruction that will then also get executed on the U pipe, because if you're only running one instruction, it's always on the U pipe. So in this kind of design, it's just U pipe just is full on, can do absolutely everything. That's a hard rule for that kind of architecture. And the V pipe is like, we're gonna pick up stuff opportunistically when we can. So that's a way to do this kind of thing, where you try to do these two at once, and like this plumbed into at a very low level, that it's even trying to find these pairs of things. And then you just try, can I run these two to completion at the same time? And if that works, great. And if not, you just do one then the other. So that's nice. And there's really not much specialization here. The UPipe really has to be able to do everything, or this whole architecture breaks. This whole idea that if anything goes wrong, We can do these in sequence, and everything on the U pipe is fairly fundamental to that kind of design. Newer in order designs don't really do that so much. They tend to also have, and like this is the same kind of thing you see in out of order process or other things. You just have a bunch of functional units. Sorry, I didn't mean to put text here. Whoops, what was that? So they're now more grouping towards these kinds of things where you actually have separate functional units with a separate design, with separate strengths, and every cycle you're just slotting these instructions into whatever pipe they can go. Daniel says in the chat, Daniel Collin, hi by the way, says they're called POEP and SOEP, primary and secondary optic and execution pipelines. Yeah, it's pretty similar to UNV pipe on Pentium. I remember that much. I just didn't remember the names. I knew it was like PQ, whatever. Like PNS. Okay, primary and secondary. Newer in order designs are more like this style, where you just have, again, like out of order processes have been doing this for a long time. We just have a bunch of execution units and like ALU 0, ALU 1, and so on. And like there's not as fixed a mapping here. In the Pentium, in the 68060, the U pipe is always the first instruction. The V pipe is always the second instruction. Like, so there's a very clear pecking order between them. Newer designs tend to for example, there's no hard ordering here. Like ALU 0 will typically be the first ALU instruction that cycle, I suppose. But like load stores, like not really something that is either before or after ALU necessarily. Like you could imagine like two instruction sequences and like imagine this is like a MIPS-like thing. So we could have, where's the mouse cursor here? We could have either, first example is you have whatever load word T0 from whatever for T1, and then add T1 at I, T1, T1, 4, and the second possible sequence would be like these two just exactly, well, not these exactly, like I need to do something different or they can't pair. Let's do T2, T2, 4, and then have the load. So these are two possible groupings of like two instructions you could conceivably run inside a cycle. Right? The first variant here has a load and then an add. The second variant has an add and then a load. And both of these, like the add instruction would go to one of the ALUs, and the load instruction in this kind of design where you have separate things would go to the load store pipe. And like the load pipe here, load store pipe, is neither chronologically, like it doesn't happen before or after ALU 0. It's just like it gets the load store instructions. You're grouping by function, not by where the thing is in the instruction stream. Whereas if you're on the Pentium, Pentium, turns out memory operations can go into both pipes. So in fact, both can have a memory operation in them. So like you can even have two loads at the same time. Like that works on the Pentium. There's no contention there. There's like the data cache can actually, it's dual ported. It's not actually, it's banked, but we'll get there. So the load cache can do two loads, two stores, whatever in the cycle on the Pentium. But if you have same example here, and I'm not gonna write the whole instruction. Well, actually, let me, like the first example would be, say, move EAX ESI plus 4, and then add ESI, 4. The second example would be add EBX 4 and move, say EAX, come on, ESI. So on the Pentium, this here in a pair, this here goes into U, this here goes into V. These are pairable, so this will actually work. And this sequence here is also pairable. This goes into U, this goes into V. Note that if you're decomposing by the functional units, the load instruction would go to the load store unit. The add instruction would go to an ALU thing. Here, the grouping is really pretty much by where things are in the instruction stream. So the first instruction goes into U, the second goes into V, or on the 6860 into primary and secondary. So that has somewhat different implications in how these things are structured. On these kinds of machines, the more modern type, you need some phase here, some clock cycle here during in the back end, where you even figure out where to slot which instruction, right? You get these two instructions in sequence from the FIFO, you're trying to pop two instructions from the FIFO, and you're trying to figure out, can I make these two happen in the cycle? Are there any conditions that prevent me from doing this? And if so, what should I do about this? Can I execute just one of these? Whatever. You need to figure that stuff out. In the Pentium design, you just always try like U and V. Like there's some tagging here that happens like very early on to let you figure out which goes where. And then you need to do a parable check. But like after these are slotted, like first, second instruction goes to U and V, that then never changes. There's no reordering stage here. There's no figuring out resource conflicts, no nothing. So the pipeline here for this kind of design is shorter because there's no extra step in the back end to figure out what goes where. And I think I mentioned this. So the Pentium pipe is also a 5-stage pipeline, actually. The original Pentium 1, so P54 up to P54C, the pipeline goes fetch, D1, D2, E, right back. Note there's no, like there's two decode stages here, but it really doesn't correspond. Like the second decode stage is pretty much what the first decode stage does in MIPS, where it's also like register file read happens here, but also like this is mem. Like mem is actually somewhere here. Like the memory access phase starts in D2 and completes in E. The address calculation and so on happens in D2, not in execute. So in MIPS, you have this kind of design where it was the MIPS pipeline, and like, just for refresher, well, this is like R3000 level, right? Fetch, decode, X, mem, right back, and the later MIPS, mem, this is a bit hard to parse. The later MIPS designs kind of riff off this, like they're sort of still based on this. So there, the memory operation starts after the execute cycle. In fact, this execute cycle for memory operations does the address calculation. Like here, this ESI plus 4-bit on x86, or what would be the corresponding addressing mode on MIPS. On MIPS, that part of the calculation happens in EX, and then the actual memory access happens here. On the Pentium, you cannot share the adder from the execution units here. Like, you need 4 adders in this design. And like these are actually, like these in the D2 stage are actually more complicated than those in the execute stage, because these have to deal with complicated addressing modes. Like x86 lets you do stuff like ESA I times 4 plus whatever BX plus 1, 2, 3. So there's a shift here of up to 3 bit positions. This tier is times 1, 2, 4, or 8. So like there's a bit shift here. Small shift, like there's only like 4 positions permitted. So it's not a giant shifter, but it is a shift. Then you add a second source, and then you add a third immediate. So you need a 3 operand adder here, you need a shifter, and like all that has to happen in D2 at the same time as the register read. And does your 2 register reads. Like generally x86 instructions have like, note this move here has a destination, it doesn't read any sources. So if you're doing like this kind of stuff, like this kind of instruction, like say if you do add say ECX, EBX, which is like something separate from the stuff above. If you're doing this, that has 2 sources, namely ECX and EBX, and ECX is also the destination. But this ECX is both read and written. So you already have 2 sources here. So each instruction is reading 2 things anyway, and like the Pentium can make this happen if it's just a pure move. If you do what you can also do, add EAX and then something complicated, like whatever, this kind of stuff here, then you have 3 sources, and this stuff cannot go in a single cycle. In fact, this can not only not pair, it also takes 2 cycles, because that one has to be internally split into first a move that only reads 2 registers, and the hardware can read 2 registers for every pipe, and then the add. Yeah, the addressing mode is exactly what you can do on 060 as well. These addressing modes have tradition. I think that goes back to some IBM machines from way back when. Like there's nothing new under the sun here. This thing you see, register indexed with a scale and another immediate is probably the most general addressing mode you can build that is generally useful and doesn't make your life hell as a hardware implementer. Like the MIPS stuff goes for the, like MIPS only has this super simple register plus immediate. Like they only do, they only let you do this kind of stuff. They don't even let you add 2 registers. And then PowerPC, for example, has addressing modes for register plus register, but they don't let you do a shift or an immediate at the same time, which is partially an encoding limitation also, but it's also like these things do make the load store pipelines more complicated. Actually, the bigger issue here is reading 2 register sources. If you're reading 2 register sources, throwing this shift in here is not that big a deal. Throwing this extra add in here as well is kind of annoying because this value has to come from somewhere and you have to do a 3 operand add instead of 2. So that stuff gets more complicated. Yeah, the Motorola 68000 has the double indirect and so on addressing modes. These are exactly the addressing modes you really don't want to have in your pipeline because having to support them makes you do weird things. And this is also the kind of thing that can kill an ISA. Like there used to be machines that had really, really crazy addressing modes in commercial architectures, and now there are museum pieces that have really complicated addressing modes. Because it turns out, like for example, on a DEC VAX, like this kind of split between front end and back end, you can't really easily do that because this thing here, the front end, has to do all kinds of arbitrary, complicated indirect loads here. Like it's not just a single instruction stream. Like you can have indirect loads here where there's a pointer in the instruction stream and you have to look at what the pointer is to even figure out how many instructions you're generating. So having that kind of complication in the front end really throws a wrench into what you want to do to decouple these, and that's why these kind of architectures kind of died out. Like that gets just too complicated to manage, and like nobody could figure out how to do really efficient implementations on the architecture budget they had. So like this kind of stuff gets more complicated. Addressing modes, the double indirect stuff and so on, when you have something here, I don't know the notation for a 68K. I know the original 68000 wasn't that bad. And the 6820 added the double and triple indirect addressing modes, which are just completely horrible. So you don't want to do that, where that's like, oh, there's memory access, and then there's another dependent memory access, and then there's another dependent memory access, and then you get the value you actually wanted. that stuff's bad. We're going to get into why that's bad very soon, actually, because that's going to be the subject of this talk, because I want to talk about interrupts and exceptions, which is exactly why this is bad. But anyway, the whole reason I came into this whole thing, in the MIPS, you have the execute and then memory pipe. So memory access is kind of after execute, and you can just use the regular ALU for this. In this kind of design, where you have memory operations happening here, you do need a separate set of adders just for the address calculation here. However, you get some compensation for having all the memory operands ready and waiting for you in the E stage. Because it turns out that the scrappy Pentium, which is with its also 5-stage pipeline, has a couple good ideas in here, and the way this whole design here works out that the simpler MIPS R3000 and R4000 does not have. And we're going to see some of that today. So older designs fix slotting and just UV pipe or primary, secondary. Newer pipes tend to just have a bit more slack here, have something that figures out which pipelines are available, which pipelines operations should go into, tries to maybe load balance these things, and just has a separate distribution here. And these pipelines then also have separate lengths. So for example, these ALU pipelines, like basic integer ALU is whatever, like that's usually 1 cycle. You slot all the fast instructions there. Adds go in here, shifts probably, binary logic, that kind of stuff. Load store, probably at least 3 cycles. Sometimes more. Why is the mouse stuttering? All right, so like let's say that's 4 cycles. Float, like FPU, also probably at least 4 cycles or something like 6 or so. So these have variable lengths, right? And each of these has a different length. How many did I draw? That's probably something like 7. Yeah, it's 7. That's along the long side, but that stuff happens. So you just build these more, instead of having this very much tied to the instruction stream, the instruction encoding, you kind of do a more distributed thing here where you slot things separately. We're going to see why in a second. Because one issue that we have to talk about, man, the mouse cursor here is really hard to see. I wish I was something different. And I wish I knew the hotkeys for this. I need to see. Anyway, yeah, issues. I mentioned exceptions and interrupts, because that's the thing that programmers never think about. As somebody writing especially user mode software for a machine, you're very, very much isolated from problems and complexities associated with exceptions and that kind of stuff. As somebody designing the machine, that is one of the chief problems you'll be dealing with. So, for example, you have this instruction fetch here. Note that we have an instruction cache fetch from memory here. You have address translation. This address here could be bad. This could be a virtual address that's not even mapped. And you're fetching instructions from an address that has no configured mapping. Or it could be an address that's actually valid, but you don't currently have it in your TLB. TLB is the small cache that caches these address translations. And in that case, you're not going to get that result right now. And you're going to have to figure out what you're going to return to the, or what can I put in the FIFO, if anything, for the next couple cycles, because you got nothing. If you have a TLB miss, you have to wait until you know what address to fetch from, if any. And it might be that there is no address translation because the mapping is invalid. You can have memory accesses. This memory access, this read or store, like this here is a load, but this could also be a store, could be to an address that doesn't exist. On MIPS, these loads here, on most of the chips, I'm not sure if it's all that they ever built, but certainly most of them only support aligned loads in hardware. So if T1 here is an address that's not divisible by 4, we're doing a load word here, which is a 4-byte wide access. If this address isn't naturally aligned, so it's this result of T1 plus 4 is not a multiple of 4, then the machine can't execute it directly. There are instructions that can do these unaligned accesses, but regular load word cannot. So when you do that kind of access that's unaligned, that's an exception that will get reported somewhere. If you have again, address translation also happens with the memory accesses. So if you have a virtual address here of T1 plus 4 and that's unmapped, that's an exception. Or if it's just not in the TLB. In fact, like on x86, you have hardware. Like you have some hardware-defined format of this is how we're going to store address translation, which is some tree scheme. It's just a radix tree, basically. MIPS does not have that. MIPS has in hardware a architectural TLB that the OS can access. But if an address isn't mapped, just purely if it's not in the TLB even, like there's just 96 or whatever for like, the size varies. It's like the size of elements in the TLB is something like on the order of 50 to 500, depending on the chip, the architectural TLB. If you're on the larger side of that, there's a second level TLB, that's the thing that you refill. And there's a first level TLB, that's the thing that the processor actually accesses, because the first level needs to be smaller than that. But either way, there's just a small cache of address translation, and if that cache misses, the OS has to do something, has to tell the processor where that address comes from. So even a TLB miss is an exception in the MIPS architecture. This add here, note this is an add I, add immediate. It's not add I U. Quirk or interesting design feature, however you want to view it, of MIPS is that every single integer arithmetic operation, or at least the integer adds and subs, do overflow checking. If this thing here has a signed overflow, the processor will signal an exception, because that's not allowed. If you want to have something that's allowed to wrap, you have to use add IU here, which means add immediate unsigned. It still has signed operands, still does the exact same operation internally, just doesn't cause an exception if there's an overflow. So even just regular arithmetic instructions, no memory access, no anything, can generate faults. So from the chat, is address translation done on the CPU, or is there a chip on the RAM that does it? It's done on the CPU. It's very, very hardwired to the memory pipe, actually. That's where this whole TLB thing comes into. I might get into that a bit later. First, I'm going to show something. This is official, like this is the MIPS R4000 microprocessor users manual on the subject of interlocks and exception handling, which is kind of cute. I'm not going to read the whole thing. They have this whole category here. Like there can be faults, like something goes wrong, right? And can get handled by software, in which case they're referred to as exceptions, or they can get handled by hardware, in which case they're called interlocks, and there's like stalls and slips. This is MIPS terminology. Sorry, from the chat. Is it done by the same registers that do regular computation? That's not what register means. Like there's also not context switching. Like I think you're confused about what these things mean. Like this is like what I'm doing here is not really an introduction into how these machines work. I'm going a bit more in depth about like what current pipelines look like, but I'm not explaining what a TLB is or how address translation works. That's sort of out of scope. So if you don't know at all how virtual memory access works, this is not gonna be the right stream to look at, sorry. Like it's just like, I could go into that, but that's a whole different tangent, and like I don't wanna, like, that stuff, like the fact like there is address translation, there's stuff like TLBs and so on, is well explained elsewhere. So I recommend you look at that kind of stuff. Sorry, it's a bit disappointing answer, but like I need to make sure not to get too rambly. So back to the interlocks installs thing. So interesting thing to note here is like what programmers tend to do is like whenever anything goes wrong with CPU, whatever, it's like, oh, it's like exceptional or whatever, or there's a stall, right? There's different kinds here. So like what MIPS calls a stall, they say here, are resolved by halting the pipeline. In the Pentium design, these are called freezes. That's when you just literally say like, okay, nobody move, something went wrong, let me figure this out, and you just halt the entire machine until something that you're waiting for is resolved. Like some pipeline stages may be doing work, but nothing advances through the pipeline. And there's slips, which require one part of the pipeline to advance while another part of the pipeline is held static. So in this kind of thing, you might say like, oh, a slip is like the FPU is not accepting any new instructions at this time. Like you have something, whatever, where might this kind of stuff happen? Say you have something that's designed to do single precision floating point operations at full throughput, fully pipelined. Like yeah, something like say the cell's SPU. Like there have some hardware that's built, it's even about the right length here with my 7 cycles. Like there's something like a 6 cycle FMA pipeline, maybe a write back stage. So this is built for full speed, single precision computation, but it also supports doubles, but it does so by going through some of these stages multiple times. So like instructions stay in these stages longer than for a single cycle. And for that to happen, you have to just kind of like, while it's going on, you have to stop accepting new instructions here. Like this first FPU cycle just has to, like, if you have a double instruction, it can only, like, there's some number of cycles here where all these stages after here, like there's data being shifted through here, and that does work and it's fine. But the first FPU stage just kind of says nobody may pass here, nobody may enter right now. We just need some time. So like parts of this here are advancing, and like older instructions are still completing on time, but newer stuff is kind of blocked until this hazard is resolved. That's what MIPS refers to as a slip. So in the stall case, absolutely nothing in the pipeline advances at all. In the slip case, like usually the older stages of the pipeline make forward progress, whereas the earlier stages of the pipeline are halted. And there's some cycle in the middle where stuff happens. This is MIPS R4000, and like this is just list of all these conditions. I love this list. So this is the R4000. It's a classic, absolutely classic RISC CPU. It's like, I think one of the first 64-bit microprocessors ever. It's like 92, 93 or something like that. So like you think of these like, oh, MIPS is like only relatively few instructions, super simple pipeline. You like, this is the list of internal stalls, slips, and exceptions that exist in that pipeline. I'm not going to go through all of them. It's just like where these things are even detected. Like stall here, ITMs, that's like this happens in the instruction second state. This is an ITLB miss. This happens when like during instruction fetch, it notices like, oh, that address isn't in a TLB. And then it needs to like, damn it. I need to just halt progress. I need to clear out the pipeline. I need to jump to an interrupt handler in software that's going to do the TLB refill. This ICM here is an instruction cache miss. Note the TLB miss is here. That's the first cache that's being accessed to find the address translation. The instruction cache miss, like this is after the data is read. It reads some data from the cache. And like we're in the register file read stage. Like the first 2 cycles, it just reads some data from the cache, and then it checks. The tag check happens here, where it figures out, like, did I even read the right data? So like that happens after the data is already there, which is typically how these things work. I went into that a bit last time with the virtually indexed, physically attacked caches, which this chip also uses. So that's the whole pattern. You get the data first, and then you figure out what the right data to use is, if you even have the right data. So the data is read here by the end of the IS cycle. All the data is read. You just don't know whether it's the right data. And the instruction cache miss signal is actually generated after the cache access is done. There's no stalls that happen in the EX stage. This is to do with some, like, this is sign extent thing. I'm not sure, like, it's probably address propagation, something like that. Like, I don't know what all these acronyms mean. They're explained here. What was CPBE? Probably coprocessor. Yeah, coprocessor, possible exception. So there's all these kinds of things, like, in these age stages where everything could possibly stall. Slips, note, these are all in a single stage. If there is a possible slip in the instruction, that's all detected in the single register file stage, register file access. That's the only stage something can ever slip in. Slip is the thing where they discover, like, oh, we need to insert an extra cycle here. So for example, LDI is, I believe, the load interlock. Let me see, where's that? Load interlock, yeah. So because they actually have the pipeline here, so I don't have to draw this out. Execute is here, like this is instruction, fetch, first and second, decode and register file access is here, execute, data first, data second, tag, check, write back. The loads actually happen in here, data first, data second, like after the end of this cycle, after the end of the data second cycle, the data is known. We've fetched the data from memory. But if you have, say, a sequence where, like, let me say you do, you load T0, let's load it straight from T0, and then you add, like, you're fetching a pointer and adding something, right? Doesn't matter. The very next instruction after this load word is an add. The load word finishes in this cycle. The add needs the data in this cycle. So like there's like an extra 2 cycles you need to bridge. You can get from the end of the execute cycle for the first instruction, or like if you have 2 back-to-back integer instructions, you can get from execute to execute no problem through a local bypass. But there's 2 extra cycles here if the result is from a load memory. So like this load here happens logically, like it's complete 2 cycles later than an addition is complete. So if you have a load followed by an add, there's 2 cycles where you have to bridge because the data isn't actually available yet. And that's the load interlock slip. So basically if you do a load and immediately consume the result, this slip here inserts effectively knobs into the pipeline. All these slips basically add extra knobs in the pipeline. For later instructions without consuming anything from the instruction fetch stage, when they detect that these conditions are happening. And there's like, these are some to do with multiply and divide, which take longer. There's load interlock. This here is to do with the shift, I believe, because the shifter in the R4000, if I remember correctly, could only, like, it's a 64-bit processor, but if you want to shift by more than 32 cycles, it takes an extra clock cycle. Let me see if I remember this correctly. Variable shift or shift more than 32 bits. Yeah, that's a shift slip. So like some shifts take longer than others. Some shifts take 2 cycles. And finally, exceptions. Note, instruction TLB miss was detected, the stall here was detected in the IS stage. The ITLB exception is generated 1 pipeline stage later. Like I said, it's explained somewhere what these are specifically. Instruction translation or address exception, and ITM is the ITLB miss, right? Instruction TLB miss, yeah. So some of these things are detected at some stage in the pipeline and then get turned into an actual exception later. But notice, There's all kinds of exceptions here, which just trap into software that are generated at all stages of this pipeline. Just to give some examples. OVF here, that's integer overflow. That's the one I talked about. Inter here is actually that the interrupt line on the processor. Like, the processor has an interrupt line that you can use when the device needs to flag it to wake up. Instruction ECC error. Like, this is when there's this data corruption in the cache, bad stuff happening. Like, this is going to be floating point exception thing, data TLB miss. TLB modified is when you try to do a write to a page that's flagged as not dirty, I believe. If you just try, if you write to a page that's flagged as not writable, it's just an error, and that's, I believe, will give you just a regular ITLB exception. But if you try to do a write to a page that's flagged as writable but not dirty yet, I believe you get this one. Like, there's all kinds of things here. Point being, even for something that's considered a very simple design, there's a lot of these possible stall conditions, and they can all happen for any instruction. Like, there's a million possible ways this could go wrong that happen in different stages of the pipeline, and that you need to do something about. So this is not necessarily all nice and easy. This is actually something, and like even these stalls here, like I mentioned this part, having these stalls in here is kind of, the actual stalls that freeze the pipeline are an issue. I said, what the Pentium calls freezes. Slips here, this kind of thing is nice, because you can see this is all detected in one stage, and it's basically just you need to freeze this part of the pipeline that keeps giving you new instructions. You need to tell it to back off on this. If there's a FIFO in between you, so if you have this kind of design, you might not even need to do that, because you're just not consuming from the FIFO, and eventually the FIFO will fill up and there's back pressure and this unit stops fetching. But there's nothing you directly need to do. You don't need to tell it anything. So the slip kind of thing is sort of nice, because you just basically add extra knobs here to the rest of the pipeline, and they sort of go through after that unhindered. This kind of stuff is okay. The stall thing, where say you detect in the TC stage of the pipeline, tag check, the DCM is data cache miss, I believe. Yeah, DCM is data cache miss. That you missed the L1 cache, and now you need to do an L2 cache access and so on. And now you need to halt everything and possibly re-execute instructions. That's not. There's multiple problems with that. First, this whole, like, you can't just you can't just halt the pipeline. That's easier said than done, because like this whole thing, I said, it's like this, any stage or any of these stages here, 1, 2, 3, 4 stages that could flag stalls, all these 4 stages need to be connected over some giant wire that can tell everybody else to just please stop. Like, this signal is critical, because like there's long wires here, and just dropping everything you're doing and being able to restore it later is not that nice either. So for example, one thing I mentioned with the loads earlier, it's like execute is here, load like DEFDS. This is when the data is done. Like, at this point we have decided the data, but we haven't checked yet whether I just gave you the right data, or maybe it was a data cache miss and I just gave you garbage. As soon as DS is done, that's the 2 extra cycles for the load interlock I talked about. We give that data to whoever wants to consume it. So this load word T0 from T0, this will do a cache lookup. That line might be in the cache or it might not be. it just grabs some data, and before it knows for sure whether that like data was actually there, it already has forwarded that data. Like just like if that data is in the cache, it's gotta be in this location. Immediately forwards whatever's in that location, and only then after it does that, it checks whether that's actually the data you asked for or not. And this add instruction will immediately start with bogus data. That's why this here with the data cache miss is a stall. There's fun diagrams here. Here an example of pipeline backup occurs in the data cache miss, in which late detection of the miss causes a subsequent instruction to compute an incorrect result. So this thing here is actually a data cache miss, but it's already forwarded like the result of that wrong data cache read to this add. So what actually happens is like you have this execute thing here, like this instruction here, like data first, data second, whatever for the first read. And as soon as that first read is done, it does the execute with bogus data. And at the same time, the processor does the tag check, and then it figures out, it's like, oh, I just handed that add instruction completely bogus data. Well, that's not good. So at that point, the cycle here goes into stall. It's like, oh crap, gotta do something, like second level cache lookup, whatever. And like at that point, it's like, okay, I guess I need to say replay the load. Like you do some fill here, like fetch it from second level cache, whatever. Then you start replaying this part of the load. It goes to data fetch, data second again, prime the pump here. Like at this point, it's like restart two, like this here is like a countdown. Restart in 2 cycles, restart in 1 cycle, where it just has to put instructions back in the pipeline again, because everything here has to back up by 2 cycles. Like we just have to re-execute part of these instructions again, because when we executed them the first time, we just passed garbage through the pipeline. So this here has like this add instruction here that's happening that's dependent on this load. The first time it executed just fine, but it produced garbage. And then we needed to rerun, register fetch, execute again, this time with the correct data, and then the instruction can complete through. So like in the cases when there's stalls in the R4000, there's this whole complex process that has to happen. And I'm not even talking about the implementation side of this. It's like, oh, you're just assuming when you say like, oh, a given unit stalls. The implicit assumption is that you can just hold right there indefinitely. But like, you need, like, there can be operations in flight that you need to store data to be able to retry them again. So you have these things called skid buffers that are used like while you're trying to like, okay, you notice a stall needs to happen, and now you have some data that you need to stash somewhere, and there's extra buffers for that need to be provisioned in the pipeline so that you can actually stall when you need to stall in a way that allows you to do the startup again later. So there's all these kinds of problems that you never really think about in the hardware. It's just like, if you notice something has gone wrong, there's a good chance that something went wrong like a cycle or two ago, and you didn't notice until now. And then you need to restart some instructions, re-execute part of this. There's all these, like, I'm not going to go through all these. It's just like, you see all these cycle diagrams of like when exceptions are detected, when stuff is forwarded, and stuff is complicated. I was saying stuff is complicated. Like here's like timing diagrams on when stuff goes to memory and so on. So that's the kind of stuff you don't really think about as a programmer, because basically everything you do is all this is either fixed up by the hardware behind your back, unless whatever the hardware is doing is not working, and then the OS needs to do something, or the app needs to work around if it's really bad. But mostly you don't notice these things. And the other thing is like, say this here is not just a data cache miss, it's actually a TLB miss. So this address translation is something the processor doesn't have. In that case, this load here, execute once, executes the first time, notices this address is not in the TLB. So then it generates an interrupt. It needs to jump to a specific handler in memory. Like there's a separate vector for this. Like, let's go there. CPU exception processing. There's these awesome flowcharts. That's why I love this manual. Where are they? Like this is just what gets set up on which exception state, what the registers are. Like there's special system registers that tell you what exception happened. And here, this is what happens on reset. This is what happens on cache errors. Like all these kinds of things that get initialized. And the best thing here is, it's some pages from here. Where was it? Yes. Exceptions other than reset, soft reset, NMIs, non-maskable interrupt, cache error, which is like an ECC error, or first level miss. It's like, there's this whole flowchart. Set watch register, set floating point control status register. N high, this is something to do with the context registers for TAB invalid and refill. Context, set cause register, exception code, set bad virtual address. Looks at the exception level register, which is like, am I already, like, because you can have an exception occur while you're already processing an exception, and what do you do there? Here, check if exception within another exception. If it is an exception within another exception, complicated things here. Is the instruction in a branch delay slot? Yes or no? It needs to do a different setup. Then it needs to figure out where to jump to. This PC go to blah, blah, blah stuff here is jumping to an exception handler. This is at startup, I believe. Yeah. Like, there's a separate register here of like, am I doing bootstrap or not? Because like at some point, like this thing here, whatever's at this virtual address here needs to get set by the OS at some point. But at boot up, it's a different thing. That's a magic physical address and like all this weird stuff. This is still exception processing, general exception servicing guidelines software, right? This is what a TLV miss looks like. I'm not expecting you to look at these here completely or like understand any of this in detail. My whole point of this is just complicated stuff happens. Like for real complicated stuff happens on exceptions. Where you need to save state, you need to set up all kinds of cause bits, you need to set up context so the exception handler knows what to do. There's all these kinds of decisions about where even to jump to, and then you need to go to the right address for the exception handler, and then the OS or the BIOS, or not BIOS, firmware needs to do something. And then eventually you go back to resume this flow of execution. So lots of complicated stuff happens on these exceptions. Like if you have like, and this is not something super esoteric. This is a TLB miss. TLB has, like in this chip, I think was about 100 entries. So this can map a couple hundred kilobytes of memory. Whenever your current view of memory, like whenever you access a page that you haven't accessed before, it goes through this TLB exception handler. It needs to call a routine in software that updates the TLB. It's like, here's the translation for that page you're looking at that you currently don't know where it is. And then after all that's gone, so that's like in the handler, that's like something like 17, 18, 20 instructions, something like that. It needs to return. It needs to resume execution, which involves restarting this load. And then hopefully this time we'll go through. As a programmer, like all you ever see is like, there's only two possible outcomes for you. Either this address was valid, in which case you might page fault or it might not page fault. Like Might be that this is in virtual memory and that the OS needs to materialize the data from disk and all kinds of horrible stuff happens, but you'll never see any of this. This will just be transparent to you. All you'll notice is that some of these loads seem to take a really long time. Because of course, like there's millions of cycles where the OS is like, oh god, we gotta start disk IO and so on. So it's gonna be complicated. But like your app doesn't have to deal with any of that. As far as your app is concerned, it's just like some of these loads occasionally take a million clock cycles because, actually more, because there's disk IO involved. But mostly they don't. Mostly everything is fast. And like, there's a lot of things that people propose, like, why don't processors do this? Or why don't they do that? And mostly, or let's say 80% of these things that people suggest, like, why can't we do this? Why can't we do that? Most of the time, you just always got to ask, what if there's, say, an exception? What if we do a memory access for memory that doesn't actually exist, that's not mapped? What if we do, what if there's an interrupt? Because sometimes you have interrupts and you don't want hardware instructions that take super long, so you need to be able to abort these. There's all these kinds of problems. There's also, like, you mentioned this whole bypass network in the last part, and about how most data you ever access actually comes from there. So then you can go, it's like, okay, if basically all we're doing, like almost all the data we ever access is coming from the bypass network, why do we bother with this register file at all? And I actually mentioned how Intel used to build processors where the actual register file was relatively narrow, didn't have that many ports, not as many as you would expect a processor with like whatever 3 execution units or what they had to have. Like you would have expected this thing to have something like 6 read ports, but it actually only had something, I think it was 3. And the reason they could do that is because most of the operands typically come from the bypass. So you can go, okay, if we're mostly bypassing these things, why do we bother with writing back things to begin with? Like, hey, say this load here. I'm doing a load of T0 from something, and then the very next instruction, I'm immediately overriding T0 again. It's like, why are we even writing this value of T0 to the register file? Because like the very next instruction is gonna override it again. It's like, basically it just means like this add instruction here is gonna pick up this value from the bypass, because like already mentioned, like we forward that as soon as possible. Like we definitely don't wait until this value of T0 that comes from the data cache has been written back to the register file before we hand it to the add. We immediately go from the bypass to here. And so like, why do we even bother writing this to the register file to begin with? And the answer usually in a CPU is because things like interrupts are allowed. Like, what if you have an interrupt like after this load has started, but right before we start the add instruction? That means there might be a long ass time between this load finishing and this add starting. And like if there's this kind of unpredictable interruption, and interrupts can be due to external things, it can be due to a page fault, but it can be something else, it can be from something another instruction did. It's like every instruction has to assume on a CPU, because there are all these exceptions and like external conditions that cause you to do this stuff, that something could go wrong with some unrelated instructions that you don't even know about. And there's just a long delay between this instruction being executed and this instruction being executed. If you assume that this T0 here comes straight from the bypass, then you have a problem if there's a big gap between the load and the add. Because if it is ever possible for there to be a big gap between the load and the add, then what's on the bypass for wherever you want to get T0 from, like by the time you execute the add, might just be complete garbage. So the register file here is where values get written back for any instruction that's actually retired. And if there's any unpredictable delay and so on, that guarantees that the data is there if you need it. You can build machines that lean very hard on this kind of bypassing. You just explicitly go like, no, we're gonna go straight from the load to this add, and we're never gonna write this value back to the register file, because why do we care? It's just some temporary, we're gonna immediately overwrite it. You can absolutely do that if you're in a kind of design where you know that between this load and this add, nothing can go wrong. There can be no exception and so on. And if you know that, this is beautiful and you can totally do this. If you don't know that, might be tricky. That's also, by the way, it's some of the, this is a slightly esoteric thing, but let me just point this out. If you're on x86, let me add an extra page here. Let's do this here, MIPS, and then I do the x86 equivalent here. Because that goes into one of the more interesting differences between the two. Say you do this here, load word t0, comma, let's load from whatever t1, and then add t0, t0, t2. Simple instruction sequence, right? We load a value from memory and then add the contents of register t2 to it, and that's gonna be what's in t0. And in x86, we can express the same sentiment, the same general idea, with something like add eax, comma, ecx, or something like this, right? We do a memory fetch from some location here. That's the load part here. And then we add that to what's currently in t0. I'm substituting t0 for eax. So you would think, it's like, there's this whole thing you hear often about like how x86 CPUs are internally, quote unquote, internally RISC or something like this, right? Like that's something that used to be something you'd hear. Because the x86 CPUs also internally turn this into a load from this, whatever's in this register, followed by an actual add. Like, because there's these uOps, right? Micro ops. Actually, I suppose it's a micro. And it's like, this will also turn into a load, then add. And like this kind of thing is commonly called in x86 parlance a load op. You can either think of it as talking about this thing here, which is a load operand, or you can think of it as talking about the whole instruction, which is load then operate. I have heard both. I'm not sure if either of these is canonical. I know that the term load ops is common. Within some circles within Intel, including people like Tom Forsyth, who is ex-Intel. Like, this is how the people I talk to used to call this load ops. It's fine. That's the term I'm using. There might be other terms that other people use. But anyway, there's a lot of brouhaha that was made at some point in the 90s that because the out-of-order x86 actually break instructions into these micro ops, so we do first a load, then an add, that because they do this, they're actually like RISC here wins a moral victory because these are RISC-ish instructions. But that's a bit bogus because first off, like RISC was a reaction to complex microcoded machines. Like it used to be that every CPU had lots of micro operations. Like every single instruction would turn into lots of micro operations. And then RISC was kind of a reaction to instruction sets like the DEC-VAX, which had tons of microcoded instructions, which would expand into like whatever, tens of instructions here, like lots of ROM that this kind of code was in. And there was like, no, that's terrible, because they were in university, they wanted to design this sort of thing, and maybe DEC had the resources to design that kind of microcode. And like, And they did mini computers, like the microcode for these CPUs. The CPUs were not a single chip. The CPU was this whole board, and like there was a big fat ass ROM that had all the microcode in it. And if there was a bug in the microcode, then you would send out a few field technicians with new ROM chips and have them replace them. If you're designing a microprocessor where all this is integrated into a single die, this is a problem. Because if your CPU is just a printed circuit board, then replacing a ROM is not a huge deal. It means you need to create a bunch of ROM chips, which are relatively cheap. If you have a microprocessor where like everything about the CPU is actually like inside a single chip, you can't just patch the microcode. Like you can't just replace the ROM with a new version because the ROM is part of the chip. You need to fabricate a whole new CPU, and that's not so awesome. And note that when Intel did put, like at some point they added a microcode update mechanism where there's a small amount of RAM, which lets them pick, like they have budget at Intel to fix something like, they can fix like maybe 4 or 5 microcode bugs easily. And after that, they start to look really, really closely at how much space they have left. They have some means to fix bugs with microcode. It's always tight, that space, because this is mostly ROM and it's just hardwired into the chip. You can't change anything. And then there's some really, really slapped on mechanism that lets them change a couple bytes in there with some patching thing. Like, anyway, like this whole microcode thing scared the RISC people, because they wanted to like design cheap chips, and like for a good reason, because if you get any of this microcode wrong and there's a bad bug, your chip is a brick. One option was to just not have this complex microcoded stuff. The stuff that you saw here for the exceptions, it's kind of like the most complicated thing you have in a RISC CPU, because like that sort of thing you really don't get around, but it's still a lot easier than what most CPUs had. Like they would have actual microcode that did these whole instruction sequences. x86 CPUs have microcode now that does sequences for interrupts and so on. And like they were just scared by the amount of code in there and the amount of bugs they had witnessed historically in these kinds of code flows. So they wanted to get away from that. It's like, why don't we just build the thing that executes these simple operations that we want to break things down into anyway, and then we don't have the complicated instructions. That's sort of one of the things that was at the genesis of RISC, which turns out that that's a pretty good idea. But then to go after that, to go like, oh, because x86s break instructions internally to these micro ops, like there's microcode or whatever, like that's RISC effectively wins. It's like, no. Just because x86 does complicated instructions the way complicated instructions have always been done since the 60s, by breaking them into multiple simpler operations, just because you decided like in the 80s that you could do a chip that just does the simple operations, just because everybody else keeps doing also complicated operations that happen to be made of simple operations, does not make this internally RISC. In fact, the fact that you have a CPU that actually has hardwired decode logic to accept these kinds of things, where you have an add with a memory operand, means that it's pretty much the opposite of RISC. Like that's exactly the kind of thing that RISC didn't want to have. But anyway, that was just sort of random bonus rant. But like there's many really, really good ideas in the late 80s RISC designs. But I don't like the RISC religion around them, and like even people that are really smart and have been like even technically involved a lot, like David Patterson, is prone to saying things like this, and I just shake my head, because there's just a lot of revisionism about what RISC is or isn't, and it's like the definition. It's just like, yeah. Let's move on. Anyway, the point I was trying to make here originally, and why I brought this up. Sorry for the tangent. If you have this kind of instruction, this instruction internally has a load and then an add. So it internally expands into a load and then an add. But there's an important difference. Namely, this load here is fully internal to this instruction. So when you say you execute this instruction, that means you either do both of these things, both load and then the add, or none at all. There is, per definition, you can't abort in the middle of this instruction. Either this add and then load pair goes through completely or it doesn't go through at all. So when I said that in this kind of situation here, you need to be writing this T0 here back to the register file, because you might conceivably have a situation where an exception happens between them. If you decide at the architectural level, like, no, these two instructions, like if I detect this pattern, say, or if I have an instruction that encompasses that pattern of load something, then do something with it. Either of these. If either you detect like this sequence of two instructions and say, I always execute these two back to back, or I don't execute any of them. Like I don't allow the execution to ever halt in the middle here. Then you can actually say like, okay, this thing here never gets written and it stays on the bypass. Like this is a temporary value. We need a temporary here, like this, because we need to, like, from the way the instruction set works, we need to give a name to the value read from memory. But it's purely a temporary thing, and by the time this instruction is gone, like this value here has disappeared, because the only name it has is T0, and we've just written something, we've just overwritten T0 with something different. So you can design a risky CPU, and in fact, like RISC-V does exactly that kind of thing. Like they have an instruction fusion, like they have an instruction fusion mechanism, yeah, that can, like, I don't think they've proposed this specific pattern, but they can actually decide that no, these two here are gonna be effectively one instruction, and are gonna be executed as such. And that allows you to skip writing back some data, and that allows you to just internally forward these things. So there is a difference between writing these out in code versus just implicitly saying like, it's an implementation detail that I do a load and then an add. Because it boils down to an interface thing. If you say, my model is that instructions execute one by one, and like I'm gonna execute these one by one. If you can't rule out that you ever stop here, then you need to make sure that your execution works in a way that things still work if you abort between here and here. So this exact problem of where exactly instruction boundaries are, and what kind of state can be visible to users and what kind of state cannot be visible is kind of a big deal. And like this whole thing, like, why do I care whether this is from the register file or the bypass so much? Turns out this kind of data movement is where a lot of power goes. Like getting data from here to here and back is like from load store units, say, to the register file and back. Just having all these writes of data that you never read again, that's kind of power expensive. So you would like to get rid of some of this if you can. And like that's something like, for example, GPUs do this aggressive leaning on bypassed operands a lot more actively, because GPUs generally have an execution model where there's no exceptions. There's nothing that can go wrong in that way, really. Like there's absolutely no assumption of a virtual memory model like not just x86, but general purpose CPUs, where it's assumed like there's some of these pages might not be present, but you want to be able to transparently abort and like resume precisely where you were, where you left off, and have stuff just work. GPUs, DSPs, these kind of chips typically don't have this type of model, and they have a lot more freedom in how they execute. And then you can pull these tricks. You don't need to write that data. You don't need to send it across a chip. You just bypass it between instructions, and things are more efficient. So, that's sort of, I guess, my main point I wanted to get at with the whole exception thing. And also a bit like details of like exactly how stalling does or doesn't happen. I don't want to get into too much. It gets very, very specific to a particular chip and so on. But just the idea that you need to have this notion of like, oh, like there's exceptions. Like this add here, like if this is an add u, actually, like, or, well, let's say this isn't regular add, like regular MIPS add, which can also generate overflow exceptions. So like, as designer of a chip, you have to think of every instruction, not just about the happy path. The happy path where like, oh, all the loads hit in the cache, and like you only ever have TLB misses, and like there's never any external interrupts, and there's no overflows. Like everything is good. That's the easy part. That's the part that's fun. The tricky part is things like exceptions and what kind of state is visible. And that turns out to be the tricky part. And that turns out to be where the potholes are. So for example, there's a couple places in x86 where they really dodged a bullet. There's this whole thing. There's a very, very CISC-ish rep. Like, let's say rep move SD. Which is like this implicit loop thing. This is basically, not actually sure if it's a, I believe it does effectively this. I'm not sure if this is a while or a do loop. While ECX is not 0. Loads, move temp. Like this is not an actual register. Like this doesn't overwrite any actually visible register. This is some internal temporary. Move temp RSI. Or actually I'm doing 32-bit in between here, so say. I'm using ESI and EDI. Move EDI temp. Add ESI 4. I'm running out of space. Add EDI, comma 4, sub ECX, comma 1, and loop. It's like, that's like, this is semantically what this instruction does. It's like, while ECX is non-zero, it keeps loading a word pointed to by ESI, writes that load to whatever's pointed to by EDI, increments both pointers by 4, subtracts the count, 1 from the count, and then repeats. This is a complex instruction, which is built out of simpler, already complex instructions. Move SD, like these 4 instructions here, like move temp ESI, move EDI temp at ESI 4 at EDI 4. That's a move SD. Rep is this whole, implicitly wraps this loop construct with a sub ECX 1 around it, sort of. So this looks like an CPU designer's worst nightmare, because this kind of thing is like, if you have, say, this add here, that's still nice. Because it's just an add, right? Like, and this is like, this here is one memory access of a known fixed size. It's like, it's all good. Like you can turn this statically into one load, then one add. It's all good. You can deal with this. This stuff, it's like, you have an unknown number of loads and stores here. That depends on what's in a register. When the front end decodes this stuff, it has no idea what's in that register. Like the front end has to eternally expand this into this kind of loop. And there will be magic internal instructions, so-called widgets involved that do this kind of stuff. But there's one saving grace here, which is that A, this is encoding an operation that is
probably something that might be worth optimizing for the CPU. So, okay, you can wire this up to some kind of block move engine and maybe do this more efficiently than you could do with regular instructions. So maybe there's some win here. Like this might be something you want to accelerate. And like, if you just have this broken down into individual operations, it might be tough. Like detecting that somebody is trying to do a memory-to-memory copy is dicey. Like this sort of peephole thing of like looking at two instructions in sequence, maybe doing this in the decoder while you have the instruction bytes and figuring out whether you can do this sort of fusion thing is one thing. Looking at a sequence of like 4 or 5 instructions and like trying to figure out like if there's a branch in there, if you can do this as a move is kind of tricky. It's like having this be front loaded is like, oh, I want to do a block move, and having an encoding for that is probably not the worst idea. But the important thing is this move SD thing here, this rep move SD thing. The tricky issue, again, is always the question you should ask, what if there's an exception? What if either this load or this store, for example, is accessing memory that's not currently mapped and there's a page fault? And luckily, the instruction is designed the way it is. Because this whole thing, if there's an exception, it'll just have part of this operation done. Like, because this instruction is internally defined to like every single iteration, it increments ESI and EDI by 4 and subtracts 1 from ECX. Every single iteration. That's how that instruction is defined. That's probably just how they did it on the original 8086, or well, this version with the MoveSD is 386, but that's probably just how they used to do it. But the fact that the instruction is designed in exactly this way turns out to be crucial, because it means that if there is a problem here, if there's a fault, if there's an exception, all these registers happen to be set up in exactly the way that you need them to be set up to resume the operation by just restarting the rep move SD again. Like, you can just do this. You can just say, like, okay, if something goes wrong, then ESI and EDI are pointing at the location where stuff went wrong. And ECX is however many iterations of the loop are left. So you can just figure out the problem as the operating system, fix the problem, and then just re-execute this rep move SD and stuff works. Again, it's kind of my punching bag today. There are other ISAs, like VAX. I'm not going to go into how VAX works today. It had instructions with this kind of like, oh, unpredictable number of memory references, complex stuff going on and so on here. But they were defined in a way so that all this internal state was internal to the chip and doesn't get written back to anything. So it's just this crucial distinction that rep move SD happens to be designed in a way that it's resumable. By just re-executing it. That makes all the difference. This here happens to be easy to support. The operating system doesn't need to know anything about this. And whatever microcode sequence you do for this rep move SD just needs to be implemented in a way that if something goes wrong, this state here, ESI, EDI, and ECX, get set the way they need to be so you can resume and everything is fine. VAX had instructions where this kind of stuff happened, where you had lots of internal memory accesses. They had like this kind of thing, string instructions and so on. It was an unpredictable number of memory accesses, but all this state here was completely internal and was not visible to anything. So that meant like, oh, you're doing this block move, whatever, you're trying to copy 256K of data. Somewhere in the middle of the 256K copy, something goes wrong. And there's no mechanism in the CPU to tell you where that was. So at that point, the OS gets a flag and like, you gotta re-execute this rep move SD completely, do another full 256K block copy even if the problem was earlier. Or maybe you gotta look at the instruction, decode it, and figure out what you need to do so you can resume at the part where it left off. It just gets messy. And so turns out there's no one good solution here. In this case, with the add, it happens to be very, very useful. Where's the mouse cursor? Here. In this case, it happens to be very, very useful to have the instruction designed in a way so that this one temporary for the load is invisible, because it allows you to do things that you'd rather do that you otherwise can't if this is visible. In this case, this is exactly the opposite. Because it does a long sequence of dependent operations, the fact that this state here is visible happens to be the right thing, because it allows you to resume this complex sequence of operations at the place where something went wrong, rather than retrying the whole thing. So VAX has something like, think there's instructions that can do something like 6 memory fetches, I believe. I believe that was the number. All of which can be unaligned. And all these need to succeed at the same time for the instruction to ever complete and ever make progress. So that's another of these cases where the way this is designed makes a big difference. Like sometimes it's good to have these internals be hidden, so you can do smart stuff like, internally bypassing these things without ever writing them to a register file that you otherwise couldn't. And sometimes you want it to be exactly the other way around, where having the state in a way that allows you to resume is good. Point being, this stuff is hard. And there's no one recipe. In general, the risky idea, or not risky, but risky idea of breaking these things down into smaller primitives and just having a simpler CPU that's easier to design is not a bad idea. But like you get lots, especially like it's certainly by far the easiest way to design these chips. I mean, that was part of the motivation. Like Patterson and Hennessy were both university professors. If you want to have a chip that you can design with a bunch of smart graduate students in a semester, by all means build a RISC CPU. Otherwise you're never gonna finish. And that's for that reason. It's also why it's very popular to talk about, like, say, the late 80s style MIPS or similar pipelines in university courses, because that's something you can reasonably cover in a semester and give people an idea of how they work. As you get towards more complicated capabilities and so on, you start looking into being able to fuse these two things to get more complicated operations. Doing these internal operations that save power and like that kind of stuff, these optimizations, does start to become more attractive. And that's part of the reason why x86 hasn't died the flaming death that people were predicting it would die in the 90s. Turns out that a lot of the mistakes that are really, really, really hard to recover from, like this VEX thing of just having tons of really complicated instructions that nobody has any idea how to execute, like, weren't really present in x86. x86 has many, many, many historical warts that are not really pretty, but it happens to be designed in a way, probably by accident, that this front and back end separation is totally viable, and that you can do all kinds of neat tricks that are actually useful. And the encoding is not the most compact. It's certainly not optimized for size, but nevertheless, it is more compact than a lot of the basic RISCs were. And again, using the instruction cache better is nice. So x86 is absolutely, like, from an instruction set architecture design point of view, is absolutely just this weird mixture of accidentally good and accidentally bad ideas. And it's just like, I mean, at this point, like, everything has been tried in there. But it turns out that the basic design is amenable to a lot of things that many other designs weren't. And a lot of this boils down to really subtle stuff. For example, x86 happens to be a lot more attractive for out of order execution than the Motorola 68000 series was, for really, really stupid reasons. Mostly to do with the fact that we mentioned this earlier about how 6860 had these annoying double and triple indirect memory addressing modes, which, again, if you think about exceptions, that you're chasing the sequence of like 2 or 3 pointers. The first access can go wrong, the second access can go wrong, and both of these need to go through for that load to complete. In x86, you don't have that problem. Like, there's only ever one memory access of that type in an instruction. The worst is like move SD, which has a single load and a single store with the most simple addressing mode. So x86 doesn't have the really complicated memory addressing modes where it's like, oh, what happens if there's an exception on the first load or the second load? It's like all that stuff gets more complicated. x86 doesn't happen to have that. That helps. Another way that helps is like there are some problems with how both of these 68K and x86 both have flags registers. Very common thing. In many architectures, most RISCs try to not have flags because it turns out to be easier not to have them. Their flags are kind of annoying. Turns out that most instructions you care about in x86 write all the flags, and the rest basically, for the most part, break down to like 2 parts. Like some of them write this set of flags, and some of them write this set of flags, and you can just sort of do nice things with how you handle the flags. The 68000 series, the flag situation is more complicated because there's very different subsets of instructions that all write different sets of flags. Turns out flag renaming for the 68000 is a lot more complicated than for x86. So that's one complication for out of order 68000 that x86 never had to deal with. Interestingly, ARM 32-bit also has very complicated flag handling, has the same lots of subsets problem, and x86 doesn't. x86 only has this problem really for one thing. x86, that'll be, I think, my last example for today, just to show you a final example of like boundary cases and like where you can go wrong with instructions. It's one of my favorite examples. Let's do this. Shifts. So let's do a very basic thing first. Shift right. Let's do EAX by 1. It's simple enough instruction, right? Turns out that shifting right, EAX by 1, or just a register by 1, is a different opcode from like not just a different constant, like an actually different opcode, different operation code. Say 5. Like this here is a more general, like this here was introduced in the 286. Well, not the EAX variant, that's 386, because I'm talking about 32-bit registers here. But the form here where you're shifting by any constant other than 1 was added in the 286. That did not exist earlier. And the 886 only had the shift right and left by 1. But there's a third form of shifts, which is to shift right by CL. CL is like this count register, has a special role here in the move SD thing where like ECX stores the count. Like that's just, CL is the low 8 bits of the same register. So this whole register is used by lots of things that count. This turns out to be because the 286 added the 386 is actually the one that added a faster shifter, but the 286 added the instruction for a faster shift. So original 8086 could only shift by one position at a time. And if you wanted to do, like, say, a shift by 3, you either had to do shift right EAX by 3 or shift right AX by 1 3 times, or you had to use the counted form, which happens to be defined as while CL not 0, like, that's the sort of implicit definition here. Like, I'm just not writing the sub, instead I'm writing this with negative equals whatever. So in the 8086, there's this instruction shift right AX by CL that is defined as a loop, and it's internally executed as a loop. This instruction internally on the 8086 actually executes this sequence here in a loop. So looks fine, right? I mean, it's a bit wonky, but like, yeah, if you don't want to plonk down a big shifter, and like these, like something that can shift 16-bit for the 8086 register by anything is relatively large hardware compared to, say, an add or something. Like, if you want that to be fast, like, this requires like a barrel or log shifter. This is fairly substantial piece of hardware for a chip the complexity of the 8086. Most 8-bit CPUs also didn't have a shift other by 1 for the same reason, that it's kind of a large piece of hardware, and it sort of makes sense to do it this way. So this looks reasonable, but it has one problem. What if CL equals 0? By the way, this is something that actually changed in the definition after the fact. The 8086 did exactly what I wrote down here. It literally kept decrementing CL. If you did like a shift right with CL of 255, you bet that did 255 instructions of the iterations of this loop. They later changed this so that this was also with the 386, I believe. They later changed it so that only the last, like for 32-bit shift, only the last 5 bits of this amount here count. So like this here would not do the same thing on a 386 and a 8086. But the interesting question is, what if CL is equal to 0? Because this here is defined in a way that means that if CL is 0, none of these shifts execute ever. So, and this is the part, like this is where I finally get to the punchline, and sorry for taking so long. Turns out there's 3 answers here, or there's 3 cases. If you do first case, if, well, CL, like the bits, I'm gonna write it in this very location notation. Oops, what's that? Like, I don't know, something's funny going on with the mouse cursor here. Keeps disappearing on me. If the last 5 bits of CL are 0, then it do nothing. And literally nothing doesn't even set the flags. Flags not changed. Second case is if that count happens to be then it's as if flags as if shift right eax comma 1. I mentioned earlier this here, this form of the instruction where you shift right by exactly 1 has a different encoding from this. You can use the second encoding with a count of 1, turns out. But like this is traditionally a different instruction and it has somewhat different semantics. If this count here is exactly 1, flags are set up in a specific way, because it turns out, like, especially like this is one more of these weird things, like shift left of, let's do the 16-bit version, ax comma 1. So it was just executed as at ax. That's what it turned into internally. So it turns out this thing here sets the carry and overflow bits as if it was an add. And the shift right variant and the rotate right variants do something equivalent, where they set the carry and the overflow bits in a particular way. This variant here, like they're just, they're just garbage. Like after this here, they're not set in any useful way. So Intel always said that if you do this, like the carry and overflow bits, for any count other than 1, well, the carry bit is set, but the overflow bit is set. The overflow bit is garbage. Undefined, whatever you want. So, point being, dependent on the shift count here, you have an instruction that either doesn't change the flags if the count happens to be 0, and then it needs to return the old value of the flags for anything that comes after that. If the count is 1 or more, it does change the flags, and there's 2 possible ways the flags can be set depending on what the count was. This is one of the worst parts about x86 in terms of implementing it. And as Runa correctly points out, there's now a new instruction they added. Like as of Haswell, there's now shift right extended, which is always good. Just add more x's. You can now do this. First off, it actually lets you put this here in an arbitrary register. The old instruction form, this has to be CX. This one can do anything, can be any register, and it has a separate destination. So that's nice. That's just a bonus feature for any new integer instructions they're adding now. But most importantly, this one does not set flags. Why do we care? Turns out, if you do this instruction here, that was terrible, I'm not going to outline it. If you're going to do this instruction here, shift right EAX by CL, this internally turns into 3 micro operations on Intel CPUs now. 3 operations. One of which is the actual shift, which is basically the same as the SHRX. And 2 micro operations are dedicated to this bullshit of figuring out what to do with the flags. So, that's sort of my warning story about how something that makes complete sense on one design, one CPU, can be very, very bad on the next design when you implement this in a slightly different way. x86 has this here as a warning example. Good thing is on the shift instruction by variable. Like if this here is like, you can just special case these kinds of stuff. Like if it's an immediate, you see it during instruction decoding. So you can just turn the separate behaviors of shifting right by 1 versus shifting right by 0 versus shifting right by something else. Um, you can detect this during instruction decoding. It makes your instruction decoding more complicated, but nah, there's ways to deal with that. It's yet another ward in the many wards of x86 encoding. You just go like, okay, whatever. Having to do this dynamically, and like, because you don't even know if you're doing, say, register renaming and so on. I haven't gotten into this, but if you're renaming this instruction, you don't even know if these flags get passed through unchanged or not without looking at the data, which is horrible. So this turns out to be one obscure corner case that's just really, really bad, and that they've had to live with for a long time. AMD have figured out something to do. They probably have a patent on it, and Intel can't do it because Intel has been struggling with this and AMD has not. AMD's all the shifts are always fast, no problem. They have some magic for the flag merging. Intel does not. Intel therefore adds new shift instructions to just work around this mess. This is the kind of stuff that happens. Every instruction set architecture has dark corners like this, where the regret lives. For MIPS, it would probably, like, certainly the branch delay slots would be among their regrets as well. So like every architecture has something like this. It's like, oh god, like it's just badness happens. Anyway, that's it for material today. I wanted to do 1 hour. I ended up doing nearly 2 again. A bit more. So the goal was to talk a bit about like how these pipelines work, like how we can distribute instructions in different philosophies, and about exceptions and the like, and how that complicates things, which hopefully I gave you some idea about. And I think next time I might actually talk about out-of-order execution, or I might do memory. Probably gonna be memory actually. So we'll see. So at some point I'm gonna do another part of this, and I'm gonna, as usual, warn way too late that I'm gonna stream, but it's gonna be on YouTube, so whatever. Just if you have any questions, now's the time to ask, and like I'll finish this after I'm through the questions. Cuber Caleb asks, why did Intel decide not to use explicit destination registers originally? It's a code density thing. So how do I explain this? The 8086 is not like you could say like, oh, it's a code density thing originally. It's a bit more complicated than that still. So history lesson: the 8086 is the original x86 design. Can you repeat what you said the flaw with the MIPS ISO was? Branch delay slots. Google it. There's many people ranting about it. Branch delay slots. That one has been, that's another horse that has been beaten to death. It's definitely a regret of MIPS's. It was a good idea for the original 5-stage pipeline processors, and it kind of just made everything more complicated for them forever after. Are you going to do GPU at some point also? Maybe, not sure. But continuing with the lineage thing, so the 8086 was designed to be, I believe it was designed to be assembly compatible. Compatible with the 8080, which is an earlier Intel CPU, 8-bit CPU. So this is a really old school 8-bit CPU. This is like sort of like Z80, if you know the Zilog Z80, that's in the Game Boy, and it's like it used to be in a lot of other home computers. ZX Spectrum, ZX81 by Sinclair, all these computers. TRS-80, I believe, also had a Z80. So this is another one. Like there's these two classic 8-bit CPUs. There's the Z80 and the 6502. Like this is like what gave us the 8-bit home computer era. These two CPUs were the ones that were used for those. All these here are 8-bit CPUs. 8080 has a lot more registers than the 6502. Z80 is sort of derived from the 8080, and so is the 8086. The idea was that you could take 8080 programs, and this is an 8-bit CPU, can only address 64 kilobytes memory, all that jazz. That's where a lot of the wonkiness in the 8086 comes from, the 64 kilobyte segmented like. So sort of like forced by this stuff here. They wanted to be able to take assembly programs that were written for the 8080 and run them on the 8086. It's not machine code compatible. Like you can't run 8080 binary code on the 8086, but the idea was that you could use a macro assembler, define a couple macros, and then 8080 code would assemble cleanly and run just fine on the 8086. So this thing here was already designed to be compatible with an even older chip. I mean, this here is ancient now. This here is 70s, right? Like this year is way back. This is late 70s. This is designed to be backwards compatible with a yet older chip. And all of the 8-bits are based off what's called accumulator architectures. Where basically, not only do they not have large homogeneous register sets, they basically have one register that is far more important than every other. In the x86 case, that would be AX. That's the accumulator register. There's a bunch of things that you can only do with AX in 8086. For example, the multiply and divide, like the original wide multiplies and divides in the 16-bit subset, AX is kind of special, and as is DX. In fact, every 32-bit x86 register is special in some way, but let's not go there. So accumulator architectures originally were just when you had very few registers in computers, because it used to be, we're now in the 50s and 60s, that the memory for the registers and so on was a problem. Like these were not cheap circuits to design, so people made do with very, very few registers. And you had machines that had 1, 2, or 3 registers only, one of which was the most important register, and you had machines where you had, like, say, add 5 or whatever. Like you wouldn't even have a destination because everything would just go through to the accumulator. That's sort of where a lot of this stuff comes from. These 8-bit CPUs were sort of influenced by that kind of thing. For example, if you look at 6502, you have stuff like LDA, whatever, 42. This is load accumulator. Again, in 6502 specifically, the A register, the accumulator register, is special. It's the only register you can do math with. Like, you can do this kind of stuff on 6502. You can add only to A, not to anything else. The reason you do this, register numbers take space. Like this here is more compact. In fact, in 6502, like these opcodes are basically all 1 byte for the operation code that tells you what the instruction is and also what type the operand is. Like there can be you can also do here immediates and whatever. You can load from 0 page or absolute addresses and whatever. 8080 and so on is still sort of influenced by accumulator designs, where the A register was very special, and like this sort of bleeds into 6502 and Z80 and 8086. And these here are like 8086 is a bit more general. Is more general, but still 2 address code. what about reads? Do they go through the accumulator? In accumulator machines, yes. In accumulator machines, everything goes through the accumulator. In pure accumulator machines, some might have special instructions. The 6502 does have instructions to... I believe it does have instructions to... Like, is there... I'm not actually sure anymore. I think these exist, but maybe not. I think these exist on the 6502. Yeah, so the next thing after accumulator architectures is no difference between physical and logical registers, right? So you'd be surprised. This one here has banking. Like, this has actually like two versions of some registers for interrupt handlers and so on, fancy stuff. So like there's actually a distinction between logical and physical registers even in this generation. But yeah, reg banking, that is register banking. But yeah, it's like next step after accumulator architectures where you don't even have a destination because the destination for everything is the accumulator, is to address code where just, okay, you're putting, well, you have the stuff we know, like for x86 at EAX5, you have two addresses, those quote-unquote addresses. It's just the name, right? It's called to address code. We're like, okay, this is like, this here is both the source and the destination. And this is kind of a compromise. This spends less bits in the encoding. Like, if you need to, I'm sorry, I'm taking far too long to answer this question, but I just, you should be used to this by now. I always get off on weird tangents. The issue with the 3 address code, like whatever, say MIPS-ish at I, T0, T0, 5, it's just like if you have an instruction like say at T0, T12, T23, like there's 3 register numbers in here. Each of these register numbers is one of 32. Like just these 3 numbers, these are 3 5-bit numbers. This here is 15 bits just for register numbers right there. That's a lot of bits. If you're gonna do a classic RISC, I really need to configure this damn program so I can actually see the mouse cursor when I'm in drawing mode, because it's basically impossible to tell for me. If you're doing this sort of thing here, there's 3 register numbers here, that's 15 bits already. That's sort of why they all had these fixed 32-bit per instruction encodings. Because if you have 3 register numbers, sometimes it gets even worse if you have, say, a fuse, multiply, add. These need 4 register numbers, and now you're really losing a lot of bits. It's just a lot of bits for this. So it just makes the code larger. This stuff here is more compact because you only have 1 register number. x86 has register numbers, like classic x86 has 3-bit register numbers, and there's at most 2 of them per instruction. Well, actually, it's not quite true. We had this complicated address mode. Like this one here needs 2 registers by itself, and then you can have a 3rd register here. But mostly instructions have 2 register numbers, 3 bits each. So you're losing 6 bits on registers, and you have realistic chances of fitting an instruction in 16 bits or less. If you have this kind of encoding, 16-bit instructions ain't happening. It's just not going to happen. So that's why 68,000 and x86, both of which were designed at a time when memory DRAM was smaller and slower, a lot smaller and a lot slower, we're trying to keep the code small, and 2 address code is kind of a good compromise. It's not as constrained as accumulator architectures where you spend a lot of time moving data in and out of the accumulator register, and it really also doesn't like give you any way to express anything parallel. because everything is always tied on this one long chain on the accumulator, which kind of sucks. True address code is kind of a compromise. So 68,000 x86 went this route. If you have the encoding space, you're gonna go 3 address code, especially now. At this point, like they just like these considerations that applied in the 70s don't apply now, and like that's just whatever. For SNES, is it true that memory is faster than the compute? I don't know. I do not know. It's possible. So there was this sweet phase in the 80s, like 6502. These here ran at 1 megahertz, and they did pretty much 1 memory access every single cycle. So on 6502, like if you're writing a software copy loop on a 6402, it might not look like this, but on a 6502, memory access was definitely faster than almost any computational instructions you can have. And I believe the SNES was 65C14 or something derived, which is a sort of like modified 6502 design. So if that's based on the same philosophy, like it would not surprise me if memory access was effectively faster than compute. Because on 6502, basically instructions take, it's not quite true, but it's a good rule of thumb. Instructions take as many cycles as their size in bytes plus 1. It's not always true. There are some exceptions, and every instruction takes at least 2 clock cycles. But basically, for the most part, executing an instruction took exactly as long as it took to fetch it. Like it's just you can't, or not just the size. It's the number of memory accesses, right? This thing here has 2 memory accesses for to fetch the instruction. LDA and then this. So this is 2 bytes, and that's gonna take, I think it's 2 or 3 cycles. And then you have something more like whatever. Something like this. I think this does something useful on C64, but I don't actually remember. This increments a value in memory. Whereas, God damn it, I gotta figure out something with this cursor. I literally can't tell. Here I am. So this here loads a value from memory. And then has to increment it and then write it back. It's like there's 3 memory accesses here, just first instruction byte, second instruction byte, third instruction byte. Actually, first instruction byte, second instruction byte, third instruction byte, because 6502 is a little endian. Then there's a load at this address. Then there's the actual increment, and then there's a store at that address. So it's got to be like 5 or 6 cycles. So yeah, basically 6502 is essentially memory access every single cycle, and it would not surprise me if the memory was faster than most compute you would do. Because yeah, that was the sweet years of having fast and relatively, at least compared to what it was before, cheap DRAM in the early 80s. When we got all the sweet home computers, memory access was really cheap then. Cheaper then than it was relative to what else you're doing on the machine. Pretty much cheaper than it ever was before or since. And yeah, so like the 2 address code is just kind of a compromise. Like having the 3 separate register numbers here is nice and lets you get rid of some moves and so on. But mostly this is fine and has better code density, so it's just a trade-off. If you're gonna have an instruction cache, like if you're gonna spring for multiple kilobytes of instruction cache, 3 address code is fine. If you don't have an instruction cache, and the 8086, for example, doesn't, this thing here, 8086, had a 16-bit data bus. It actually fetched instructions as pairs, as words, so that's 16 bits at a time. So there's a pressure here to be able to fit common instructions in 16 bits if you can, because then you're going to run efficiently. And then they did the 8088, which was an 8086, but with the bus interface cut in half. And that was the thing they actually put in the original IBM PC. It was an 8088, not an 8086. 8088 was completely bottlenecked on memory at all times because they took a design that was intended to get 16 bits of instruction fetch every cycle and sandwiched a bus controller in front of it that made every access take 2 cycles. So this thing, 8088, was just always, pretty much 100% of the time, was starving waiting for instructions. If you look at like Jim Leonard, Trickster, oldschool.org, school with SK, has a bunch of writing about 8086 optimization. Mike Abrash as well. Like if you're interested in that, like 8088 corruption and that kind of stuff, on these chips, it's just not even about like making the cycle counts for the instructions. The execution doesn't matter. It's all about optimizing the code size because the memory interface was so slow. So yeah, if you're gonna do something where the amount of time it takes to just fetch these instructions from memory is a significant factor and every byte hurts you, then you want to be compact, and 2 address code is a way to do that. Anyway, hope I've answered that question sufficiently. All right. What about reads? I think we did that. Really nice to go through the history. For SNES, is it true that memory faster than the computer? We already did that. Had a DMA controller too. Everybody did. Well, all the consoles did. Like DMA controllers is like, yeah, that's something you want. As soon as you're at a point where like, okay, you actually have sufficient memory bandwidth to keep your CPU fed, as in not the 8088, then it definitely makes sense to have something that can offload so that you're not spending CPU cycles, where you could be doing something more valuable on just copying memory around. Like there's better things you can do with a CPU. All right. If we don't have any other questions, I'm gonna stop it here for tonight. Thanks for watching, everyone, and bye.